Okay, so today the topic is dimensional analysis. Dimensional analysis not only helps you to, to evaluate the consistency of the expressions, of the equations, consistency in units. Who tell me an example of units? Tell me one unit, seconds. The time, for example, is measured in seconds, days, hours, years. But in general, we call it time, the time. Which other unit comes to your mind? Huh? If we go to business, for example, land also, if you go to business, which units? Maybe the currency, money, uh, percentage, amount of people, all these things we discussed last time, no? So you remember the last time I was talking about the consistency of the units, and we talked about the COVID-19 plot, number of cases, which is number of people, and this axis is the time. No? You can see the time: February, April, June. This is in months, months. So I mean, if I do an expression, let's write. I will write here this word, the expression for the corona propagation. It was number equal some saturation parameter divided plus lambda. It's another parameter measure the rate, how fast it climbs, and this is the time. If I ask you what are the units of this lambda here, what do you reply? The time could be in seconds, days, and whatever. What are the units of lambda here? The units. Let's work on something. There is something important. This lambda is inside this expression, exponential. This is an exponential. In some program software, it appears like x. You got x of minus lambda t, which is exponential minus lambda t. Euler, no? Euler number. You know the Euler number, famous mathematician. In Spanish, we say Euler, but it's not correct. It's Euler. Yeah. Well, when I learned it in Spanish, I say Euler by the time. So the units of this combination have to be dimensionless. No units. So obviously the units of lambda is inverse of time. So for example, if time is in seconds, this should be in 1/seconds. So that it cancels the units. The combination is dimensionless. We call it dimensionless, no units. The units of this, obviously the exponential has no units, so this one has no units. And the units of this guy, A, capital A, is what you say before. Number of cases. A also has the units of N, capital N. So this A measures the saturation point, remember. The number of cases at the saturation point here. And it has the same units of this. This denominator is dimensionless in this expression. And this lambda needs to be in units of inverse of time for canceling. So this is the first step for understanding dimensional analysis. So when you write expressions, if you are in your thesis and you write expressions, it's important you specify the units you are using. Because people will say 30 watts. The result is 30. 30 watts, 30 chickens, 30 roosters, 30 watts. You need to specify what. Then, this is very important. And because depending on the units, you can determine whether it's large or small. Actually, normally, probably I will touch that next class a little bit. In some cases, especially in engineering and science, people like to use dimensionless numbers. For example, when they design a ship, you design a ship, a giant ship. Let's paint a ship here, or a plane, or a ship here. Let's put the ship here with a very primitive one. Is this one? Well, let's imagine it's a modern one. If you are a company constructing ships and you want to test the design before the construction, what would you do? You will make the ship immediately large, and test it? No, you don't do that. That's not economically viable. That's not smart. What you do is to create a prototype, a small one. And the dimensions of that prototype corresponds proportionally to the dimensions of the large ship. And how do they know that they correspond? Because they use dimensionless numbers. Dimensionless numbers, for example, dimensionless numbers are combinations. For example, if I have a distance, the units of distance, this is length, so this is length in meters, and I have and I have some characteristic dimension of the ship called capital L. Then I can create a dimensionless number. I will call it let's call it gamma, D divided L. This is a dimensionless number. Dimensionless. It doesn't have units. So it will be the same for the prototype, and it will be the same for the large ship. So that's how you do designs in large scales. You find dimensionless numbers. This class, I will not deal with this, but it's important you to know that because it can be applied also depending on what kind of research you do. For example, even in populations, for example, you want to know more or less evaluate the economy of some region, or the wealthy people at least, then you gather a few wealthy people, but let's assume that that population has millions of people, then you can create a dimensionless number which measures that small population, and you say, this dimensionless number will be the same for the large population also, and I can convert the numbers from small to large after using that dimensionless conversion. So that's why it's so important. I know now probably the concept is a little bit, but you will understand it later. And the purpose of the class is not precisely this. The purpose of this class is to understand the consistency of units and how to use the dimensional analysis for designing experiments. And designing experiments, I mean not only in physics, not only in chemistry, but also social experiments. For example, you can do experiments means anything, no? In any research field. So, well, this is taken from physics, but you don't pay attention because this is an example of dimensional analysis. Where you have length, mass, time, current, temperature, etc., many variables together. If they are combined together, each one, you assign one coefficient, and let's assume this is equal to some other quantity. Of course, the units of this guy has to be consistent with the units of the right hand side. And one example is this. This is the area, for example, area and length. Which one represents the area here, and which one represents a length? The first one, this one, upper is PR square is area. Why is area? Why can we conclude that it's area? Because the dimensions give you L square. Then obviously it's area. And this is a length because the dimensions of R is length. 2 pi has no dimensions because 2 pi is in radians actually. The radians are the measure of degrees, the angles, but that's considered dimensionless. The degrees or radians are not real dimensions. By convention, 2 pi is 360 degrees, no? So but we don't consider this as dimension, and the only dimension here is length. So this is a length, obviously. So let's talk about designing experiments. Imagine you have this, well, let's start with something. It looks like high school physics a little bit. But let's assume you have this length and you have this mass. It's the classical pendulum on the wall now. And then somebody asks you, I want to study this. Let's assume you are in the times before Newton and all these guys, and somebody asks you, try to design an experiment to see what happened when I change the length and when I change the mass. For example, if I put this mass double, or if I increase this length to double, or if I decrease the length, what happened with the oscillation rate? Then what does it come to your mind? What would you do? How would you design that experiment? Actually, I say everything, but if I want to analyze this motion trivial, what will I do? I fix some variables and I select one for changing. No? For example, I could fix the mass, I could fix everything else, the pressure of the air, whatever, and I increase the length. And then I analyze what happens if I duplicate the length, triplicate the length, quadruplicate the length, and I analyze the oscillation period. That's one experiment. Second experiment, I fix the length and I change the mass. If I duplicate the mass, triplicate the mass, or make it smaller, what happened? And this is how you start to guess what happened. Now the oscillation period is in seconds, but the mass is in kilograms and the length is in meters. How can I combine these different units into a single expression? That's challenging, no? It's challenging. Of course, we all know, I will not write because this is not a physics class, but I think you should know the response of the period of pendulum, especially when the oscillations are very small, no? Which doesn't depend on the mass actually. The conclusion is that you increase the mass. This is an example where you change the mass, you change one variable, and the oscillation doesn't change. So it means that there is no correlation between mass and period of oscillation here. But there is correlation between the length and the period of oscillation. So this is a clear example of what I was talking the last time. Today class is a little soft, but I mean the content is not so much because what comes is it could be a little bit complicated for some people, so I want to go slow in that part. Then tips to consider is the dimensions of composed quantities. For example, I have mass. This is the units of acceleration. Acceleration is what? You remember acceleration? Is in meters second square is distance divided by? Exactly. So it will be length divided time square because we use length, time, and the mass. Those are basic units. But of course, if you go to other research fields like I don't know finance of economy, as I told you, the units will be different. It could be money, currency. It could be amount of people. It could be whatever financial variable comes to your mind. Option. How do you measure the option? The price of the option. Prices. The prices of the stock. What are the units of a price of a stock? The, hmm? Uh-huh. Yeah, correct. You can also create accelerations inside the stock market. How fast the price changes, it will be price divided time square, for example. So, I mean, it's more or less the same. I mean, it's not so different. Actually, it's exactly the same. So here they are telling you, for example, if you have a composite quantity acceleration, the units are composite here. This is force, the units are composite, mass, length divided times square. Because the force is mass times acceleration. So the mass is given obviously in mass. The acceleration is LT squared, so you combine this and this in a single expression, mLT squared. If you multiply this to this, you obtain this. So at the end, the units of force are this. The same happens whenever you have an equation, you have composite quantities, then of course you you have to make the product of the units correspondingly. Okay? What is the formula of revenue, for example? Revenue of, I mean, you are in a shop and you sell. It's just a supermarket and you sell. Okay. Oh, yeah, maybe. You sell 100 chocolates. Then let's put here 100 chocolates. See, and each chocolate, the price is 2. No. This is my unit here. Macau, Aomambi. Aomambi, right? Macau Patacas. I can compare to other units, renminbi or Hong Kong dollar or whatever. But the point is that if I want to know how much money I did, I have to multiply these two guys, no? So the total money will be 2 mod multiplied by 100 chocolates. Let's call the chocolates units. Units of chocolate. Not confused with the units in general. Or let's keep the notation chocolate, better for not confusing. So of course this will give you 200 mod. Why? Because in this case, the amount of chocolate in this case particularly is not considered a unit. The only unit here is in Macau, Patacas. And if I have composite expressions, well, in general, if I were more straight, if this has some units here, I have to make the result with Patacas multiplied by the units of chocolate, for example. That will be the final units. But of course, we never measure. We don't measure like that. So technically, this is not a unit. This is not considered a unit already. It's like the degrees, the angle. The angle in physics is not considered a unit. So I hope it's clear. I have to think, for example, let's assume that you have the price square. It will be 4 Macau Patacas square. Because I have to compose the units of R1B, produce the unit of R1B is a square. If for any reason I want to calculate this per meter square, something crazy, meter square of the shop, then I have to divide by the length square, and that will give me meter square, whatever it is. If it's 30 meters square or whatever, then the final units will be 215 of v squared meters squared. These are my units. So, I mean, you have to keep consistency in the units. I always carry them, try to carry them. Because if you don't carry them, you can forget. And if you don't carry them, you can make mistakes. Like, for example, and this is serious because there was a plane. You should know that there was an accident in a plane so many years ago. I think they survived. by miracle, but it's because of a conversion of units. The persons confuse BTU with the other units, no? The ordinary units. I don't know, Americans, they like to use these British units, and the British like to keep to that unit. And then somebody in land confuse those units with the units we use in the ordinary world. I mean, exactly, the international system, international unit. For that mistake, the tank of the plane was only half of the capability, so no gasoline in the middle of the flight. No gasoline. The engines on the pilots, oh my God, they have to do whatever to keep the plane flying the most they could over the ocean, crossing the Atlantic. By miracle, they could reach the land because, of course, there are ways to keep a little bit the aerodynamics, and then but no always is that lucky. No? So keeping the consistency of the units avoid you to make mistakes in your research. Keep the units always. This is an example. Consider these quantities. S is length, dimensions of length. B is like velocity, length divided time. This is acceleration, length divided time squared. And time is just the time, the units of time. Determine if there is dimensional consistency in these units. This is the first one, dimensionally consistent. Distance, velocity times time. If I multiply this by time, what happened? Time to the -1 cancels this time, right? We can copy it here on the board. We have the first one, VT. This is consistent, obviously. I think it's consistent. I know it's consistent, the first one, but let's explain why. This is length. The units of this is length. The units of velocity is length divided time. The units of time is time. This cancel this. So length equal length. Consistent. 0.5. Acceleration is length divided time squared. And this is time squared. Cancel, cancel. Length, length, length. Everything has length. On the left-hand side, you measure in length. On the right-hand side, you measure in length. And besides that, if it's kilometers, the right-hand side has to be kilometers. If the left-hand side is in meters, right-hand side has to be meters. So you have to give the consistency, because this 0.5, this number might change depending on which units you use also. Or not this, probably the acceleration. This guy here. That number might change. 0.5 doesn't change. The acceleration, yes. Now, the second one is not consistent for obvious reason. VT squared, we can change it slowly here. The second one is VT squared plus 0.5 AT. This is length divided time, and this is time squared. Length times time is not consistent with length. And this length divided time squared, time, not consistent. Imagine you have length times time and length divided time here. So completely inconsistent. And some students in bachelor particularly, they made these mistakes. They put on the left-hand side something, on the right-hand side something else, completely different units, and they mess up everything. Prof is in Spanish. Oh, teacher or professor, sorry, it's just a minor mistake. No, it's not minor, because that's the reason why a bridge falls. And that's the reason why a building can fall. And that's the reason why a plane can crash. So you have to be serious with that. Also, ethical issues, guys. You should know that when they made the Macau-Shanghai Bridge, was it Hong Kong-Shanghai Macau Bridge is the full name. There was a guy who was fired out and maybe almost go to jail because he was falsifying the test of the material. You know, they have to test this material because these kind of constructions, they have to invent the engineering. Sometimes they have to do research to see what they do. They have to make tests. And there was a guy for 7 times, lazy. He falsified the data. He was discovered. And why it's so dangerous? Because if you don't do that seriously, you can kill many people. I mean, imagine that bridge falling and the shame of China, because I will be quite ashamed. It will be quite ashamed if that bridge fall one day. You will be everybody laughing about China, basically, if that happens. So that's very serious. I mean, this, depending on what kind of responsibility you have to take this thing serious. Then that's it. What about this one? Completely inconsistent. I will show you why. You have velocity, sine, is a trigonometric function, at squared, s. First, I will ask a question. If you see a trigonometric function like sine of x, cosine of x, tangent of x, exponential of x, the quantity here is dimensionless. This quantity has to be dimensionless, this has to be dimensionless, and this has to be dimensionless. Whatever the combination is, for example, if I put exponential lambda distance, this guy has to be in the inverse of distance units for canceling the units. But this has to be dimensional. So this guy inside has to be dimensionless. We can start from that. Yeah, because the angles are dimensionless. The angle is, degrees or radians. You know that 180 degrees is pi radians, no? Or 2 pi is 360 degrees, no? That's the conversion. This is dimensionless, this is dimensionless. But once you also have to take into account, this has to be careful also. Because it's your calculator. Some people put the calculator in radians. And then you put these values here. You will get wrong results. Wrong. Or some people, vice versa, they have the calculator in degrees, dec, and they put pi. Pi, cosine of pi, you will not obtain the right result. So even if the radians and degrees are not considered as units universally, in your calculator, it's important to have this distinction between degrees and radians because you can get wrong results. For example, cosine, if I put cosine of 2 pi, what is that? This is 1. It's 360. You come back to the cosine of 0 is 1 cosine. But if you have your calculator in depth, you will obtain something crazy, completely different. Because in reality, if your calculator is in depth, what you have to put is 360 inside. So be careful with this thing. And you believe, no, this doesn't appear in my research. You never know. At least in finance, there are cases where the prices oscillate, sinusoidal, and you have to put trigonometric functions or complex numbers. Because whenever there is complex number, there is oscillation. So be careful with that. Okay, let's check this expression first. The expression inside. I already know it's not consistent, and I will tell you why. Because velocity has units, and the right-hand side is dimensionless. For example, sine of whatever number you get, it has to be dimensionless. Unless there is a constant here, but the problem doesn't say there is a constant. If there is a constant, this constant takes the units of velocity, and then you will have to check the consistency inside. And inside, of course, you have length times square for this, and length below. So this is consistent inside, but the comparison not unless there is a constant here. So maybe you in your research I found this expression, you put equality. That's not correct. There are two correct ways to put this result. If you obtain something like that, you can do this. This is proportional to this. Proportional doesn't mean equal. It means the variation of this is exactly like that. But once you put the equality, there must be a constant. T squared is blah, like that. Okay? So, I mean, carry the units, consistency of the units, left-hand side, the same units of the right-hand side. Okay? Now it comes the most serious part of the class, and this is the most difficult. I think I reserve this for being the last part of the class theoretical, because there will be an activity in the second half. And still is no break because it's 7:45. We have time. Then design experiments. When I say design experiments, it's any experiment, no? Could be social, could be chemistry, could be who is doing business here? Business people. Well, you are not doing business. You are doing environmental science, no? Your classwork? Macasto. Okay, no, what? Who is doing PhD in business? I mean, that's the question. More properly. I understood something else. Okay. Anyway, you guys, you can do experiments also, both social or financial experiments. Even when you are trading or doing stock market, you are doing your own experiments unconsciously. Those guys who do chemistry, I don't know, somebody's doing chemistry here? You, Mikael, you don't do chemistry, no? What do you do? Mangrove. It's like DNA and this kind of thing. Okay, DNA. So imagine DNA, quite delicate. Ethical issues there. Be careful. No great catch. So obviously these guys, they have to do experiments, but most likely there are in their case, if they don't have the equipment in NAP because their campus is NAP, they can use secondhand data or send the samples to some laboratory. The laboratory do for you and they send you the results. That's another way to work. No? There are three ways to work. You use secondhand data, which is online. Anybody can have access. That's the easiest way. That's how most of my students work actually, because we don't have to fight for those ethical issues which nobody wants to deal with. The second thing is you do yourself in the lab if you have the equipment. Or if you have a computer, powerful or whatever, you can do it. Or if the experiment doesn't demand so much, it's just a survey or whatever. We explained how to make surveys last time. How to select population randomly or by stratification or by some common characteristic or so. And secondhand data, yourself, or pay to some lab. But normally, pay to some lab is expensive, and I don't know if your supervisor has the money for that. It depends on your supervisor, if he has a grant or not, or if you are willing to pay, and I don't think you are willing to pay, probably. Then it's more or less like that. Here is just an example. This is a tube transporting some fluid. P1 is pressure 1, pressure 2. And this is the length. So forget the problem itself. I mean, this could be money flowing here. If you want to see like that. Gradient of money. and the length could be, I don't know, transfer from here to somewhere, whatever. So it doesn't matter. My point is that you can generalize this. This is not exclusive from physics. So there are some, these guys are asking, how do you calculate the dependence? Delta P, so the gradient divided the length. What is the functional dependence with respect to some variables? The variables of the problems are velocity, average flow velocity, the diameter of the pipe, the fluid density, or the fluid dynamic viscosity. So you want to find this delta P divided RL as a function of velocity, diameter, fluid density, and dynamic viscosity. And you have to design an experiment for knowing what's the dependence of these variables with respect to the other. What do you do? What does it come to your mind? I want to design an experiment. And I don't want to ask to ChatGPT. ChatGPT can say something, but be careful because sometimes ChatGPT say wrong things. Huh? And also, well, you don't have to code everything. I mean, those guys who are coding, they have different kind of experiments, I think. But what does it come to your mind? There are four variables. There is one independent variable which is combined. Delta P divided L is a combined variable. First, the left-hand side has to have the same dimensions of the right-hand side. This has the same dimensions of whatever comes here. And then after, you have to evaluate how the left-hand side behave under the changes of the variables of the right-hand side. If I increase B, what happened? If I increase D, what happens? If I increase rho, what happens? If I increase, what happens when I change these variables? How does it change? That defines the function. But at the end, all the expression has to have the same units. Okay? Then what would you suggest? I want to make an experiment. I want to listen to some opinion. Anyone? Somebody? Say whatever. Something ridiculous. Doesn't matter. Remember, you have to fix some variables. For example, let's assume I am in this classroom and I want to test your behavior based on the temperature of the room, based on how much I shout. That could be another variable. Based on the intensity of the lights, maybe. That's another variable. And I can select as many variables as I wish. Then, of course, I will keep fixed first the intensity, my intensity of voice, or the volume of whatever noise I am doing, normal. And I will change only the temperature. I increase the temperature to see what do you do. When you start to sweat, you start to leave the room. And I say, I copy, okay, these guys left the room when the temperature was 40 degrees, more or less. And then I start to decrease the temperature, and I realize, these guys, this other group, because it could be different group, left the room when the temperature was 15 degrees. And then after, but nobody left the room between this range of temperature, between 18 to 28 maybe. Okay. And then now I want to study the behavior of the other variables. I can fix the temperature in a comfortable zone. I can fix the noise of the classroom. And now I just change the intensity of the light. And then if it's too bright, I see, these guys are leaving the room. When it's too bright, they are falling asleep. When it's too dark, etc. So that's why you will see this kind of plots. Look at this. Possible experiments are these, in this case. You have this independent, this is the dependent variable. The right-hand side ideally are the variables you can control. You can control them. The temperature I can control. You have to select variables you can control. Temperature, noise, whatever you can control is on the right-hand side. Then look at this experiment. This first experiment, what is telling to me? Delta P divided L and B, keeping constant D, rho, and mu. So it means D, rho, and mu are constant, and B is changing. So I am fixing all the variables, and I am just focusing in how this expression changes with respect to B. That has a mathematical way to express, of course. In the right notation will be you're exploring delta P L with partial derivative of B when the other quantities are constant, which is D, rho, and mu. You will find the textbook something like this. But I don't want to scare you with this. I don't want to write these things like that. I just want you to be intuitive. And then you realize, you do the experiment. Okay, when B takes this value, it was like this. When B was this value, whatever the value is. Something important, you have to specify the units. The units of the axis, the horizontal axis in velocities, because the velocity could be kilometers per hour, meter per second. So depending on that will be a different number. So you have to be careful with that. Some guys, I have seen theses in this university where they put the plot and there are no units. And then you wonder yourself, these guys are analyzing what? And not even in the explanation of the figure below, they say which units they are using. Or they don't explain so much. Delta P overall has also some units. Pressure has some units and length L has some units. You have to select length in what? Kilometers, meters, centimeters, nanometers, whatever. Pressure is in Pascal. Usually Pascal is Newton divided meter squared. No? So you can, Newton is the unit of force, and then you can put newtons or you can put any other kind of measure of force you wish. Then the same in other fields. If you go to business, whatever, if this is currency, you have to say, it's US dollar, patakas, RMB, whatever. You have to specify which unit you use. The point here is that this person obtained a positive correlation between the two variables. When one increases, the other also increases. And it looks like more or less, I cannot see well here. It looks like almost linear or with a small curve. No? The curve is quite small. Then I say, okay, I did this experiment. Now I want to do a different experiment. Then I come, this plot is a different experiment to this. There are 1, 2, 3, 4 experiments. 4 different experiments for testing first how delta P divided L varies with B, fixing the other variables. How delta P divided L changes with D, fixing all the other variables. How delta P divided L changes with rho and fixing the other variables. And how delta P divided L changes with mu and keeping fixed B, D, and rho. So for each experiment, you could fix different variables and you analyze the behavior of the others. Whenever you're plotting something in a two-dimensional surface like this, I have repeated this many times, but whenever you plot X and Y here, and you obtain whatever, it doesn't mean there are no more variables. Maybe there are more variables, but they represent higher dimensions. There will be a z-axis here, and there will be other axes which I cannot paint because our world is three-dimensional, so we cannot imagine, but other axes, as many as you wish, can appear. In this problem, you have 1, 2, 3, 4, 5 axes. Probably 5. It's a five-dimensional problem, probably, or 6-dimensional problem. So the issue is that you can only paint or analyze two-dimensional surfaces. One dimension, another dimensions. The others, you have to keep fixed. You have to keep fixed the other variables. I hope the word dimension doesn't confuse you. You know what is dimension in the sense of mathematics, no? One dimension, or less one axis. You can construct here one, two, three more axes here. But that's not practical because you will lose the notion, you will have a strange surface embedded in something, but it's difficult to visualize what's happening in that case. So that's why people, the most practical way is 2D, two dimensions, and fixing the other variables. At most, 3D. You can extend one. For example, I could include in this D here to see what happened. And then I do a three-dimensional plot, keeping rho and mu constant. And then I could analyze that three-dimensional surface to see what happened. This can be done in any software. Any software can do that. I will show you later the software or whatever. So I think this is clear, no? In this case, you could fix that. So how many experiments are here? At least 4 experiments they did. All of them changing different variables. And all of them keeping fixed different variables also.
I think viscosity, velocity, therefore the viscosity increase. The velocity somehow will decrease.
Yeah, that's true.
So it makes the experiment very complicated.
Complicated because it will be non-linear, no? It will be something no. So of course, ideally would be to put, in such a case, to put this one, B, and maybe the viscosity as the third axis, and then put them together in the same experiment, no? Yeah, well, that's true. Of course, you didn't study fluids, you didn't study these things, but this is general. This is applied to any experiment. So in any experiment, tell me a social experiment, for example. One social experiment which comes to your mind. What is your thesis about, actually, for example? Huh? Government study, specifically in what? Government strategy. Okay, which social experiment do you think you can do in that in that direction? Population, the amount of population in where, anywhere, or in Macau, or but what do you analyze from the population? Institutional capacity of government institutions. Institutional capacity, and which variables are you considering there? Do you have any variables in mind, like any idea? You have to think about that. Which variables are involved for measuring the capacity, no, of each institution? There must be something, or how to compare them. Which metrics? Which metrics can be used to compare them? So you can design experiments also, social experiments. But of course, since it's government and it's delicate, and maybe they don't disclose everything, probably you will have to use data which is already online or something. Whatever they put online, most likely you will have to use it, and then you will have to think your own way to analyze it. But these things can be useful also, because you could generate your own variables, then after analyze the expressions and analyze possible correlations of this type. In general, when you're analyzing a problem, it's not only two variables. I mean, it's a big lie. In calculus, you study only two variables because it's the easiest way to. And when I study calculus, the most you do is 3D, three-dimensional calculus, triple integrals, gradients, and so on. Normally in 3D, it could be in any number of dimensions, but after you lost the notion of how to imagine those things. Well, in this survey, you have to define which variables you want to measure. You have to define variables. How many variables are relevant? For example, age is a variable. Age. gender, male, female, whatever you want to put, because nowadays I don't know. Uh, exactly. That's another variable. Ethnicity is another variable. What else? Social status or degree of preparation. Social status means poor, rich, whatever. That's another variable. The other is degree of preparation, is PhD, is bachelor, that's another variable. You can involve as many variables as you wish. And then you can study how they are correlated, if they are correlated. That's a way to the surveys, they have variables. What happens is that they seldom say it, but when you start to analyze, because they ask you the age, they start to ask you many things. And at the end, that's a variable. Because when you collect 1,000 surveys and you plot each result, and you have some data you can analyze in this way. You can do regressions, you can do things, you can analyze correlations, etc. What happens if I fix the other variables, fixing the other variables to 45 years old, for example, or 43 is my age, 43 years old. Fix that variable, and then you collect all the guys of 43 and you see what happened with the other variables, which kind of correlation. Or you can fix all of them together except two, one independent, the other dependent, and see. And then you can use these plots. I mean, you can plot pairs of variables by fixing the others. Pairs, 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 pairs. Age, or I mean, the most relevant variable. There must be one relevant variable you want to be careful about. Either in some cases could be amount of money, or it could be GDP, or it could be anything. But there's always that's the dependent variable. That's the one we care about. And the others are the independent, the one which we control. We change to see what happened with this guy. So in this case, this is the dependent variable. This is the one they care about, and these are the ones we control in the experiment. So it's important to select the variables which are independent as those that we can control. We can control. We cannot control the age of people. That's true, but we can control to who you interview. For example, I can control. What's your age? 10 years old. I cannot interview you. Get out. You like that, for example. Okay, now let's go. This is more like for the class A. I don't know how many class A's are here, but I will say to everybody because it's important. Anyway, everybody can use it, I must remark. But it's not compulsory. Most of the research, you don't need it. But if you want to do a summa cum laude with all the honors or whatever, you do these things. This is what you do. Well, depending on the field, because you cannot compare a summa cum laude in engineering with a summa cum laude in, I don't know. I mean, in the quantitative level, I mean. Of course, because probably they evaluate different things, different issues, way of typing, logic, blah, these kind of things. The issue is that there are two ways to analyze dimensionless, no, sorry, expressions, or to derive design experiments and to find expressions from those experiments when you change the variables. For example, you saw here before that you did these experiments, but then what do you do then after? You have this, and then so what? What's the final expression here? You have to find it. You have to find, of course, you can start to make regressions here. First, you make regressions, and you see, this is linear, this is quadratic, whatever. And then you have to take that into account because that fixes the units of each variable, no? Potential units. Okay. There is something called Buckingham's pi theorem. Buckingham's pi theorem. Somebody hear about this before in your life? Normally, people use the other method, the Rayleigh method. I will explain the Rayleigh method on the board and Buckingham method here on the slide, because you can decide which one. The reality is easier for everybody because, well, it has its complication by itself if the number of equations is too high. For example, you saw that problem that distance is velocity time plus 0.5 some acceleration time square, right? Which is, it has the consistency of units. This is what you see in high school anyway. Yeah, the displacement for accelerated particle dynamics. No? I think you use you saw the dynamics in your school. The Rayleigh method, what they use is you take the unit here, you put coefficients. If you don't know the functional dependence of this, then you have to put n here. Let's put n1 here, because I don't know what is the power here. N2 here, N3 here, N4 here. And then let's put proportional, and then and let's call this A, this exponential. Then, of course, in that case, they start to make equations because the units have to match. Then, of course, A is equal to, this is the product, so N4 plus N3. This is one equation. Other equation is N equal N2 plus N1. And then, of course, you have the equations, and then you start to play, and then this is the Rayleigh method. This is what help you to evaluate consistency of the unit, or help you to guess more or less what is the power, how the two variables are correlated. Because if you have one variable inversely proportional to another variable, for example, but you don't know which power is that inverse proportionality. It could be to the square, it could be cubic, it could be quartic, it could be 1/2, anything. And that's important to know at the end. I mean, it's not enough knowing it's inversely proportional. You need to know the exact expression, the exact way. Of course, you can do regressions, but this is an additional tool you can use. So this is the method of Rayleigh. I will not touch it so much because it's quite simple anyway. I can send you some notes about it. I will mention this one because this is more practical, and for me it's easier this one actually than this one. Then the idea is, if you have a problem with n variables, and these variables contain n primary dimensions, for example, mass, length, and time, the equation relating all the variables will have n minus n dimensionless groups. And they call it pi. Then let's see an example for knowing more or less what they are talking about. For example, this is related to the previous problem, but of course, unfortunately, they changed the D to non-capital here, but it's more or less the same problem. So you have, the idea is that you have a function when you have 1, 2, 3, 4, 5, 6, you have 6 variables here. And then the function of these 6 variables, you know that your experiment has these 6 variables, and you are sure that there are no additional variables. These are your variables. You check it yourself, and you realize that when you change one, there is some correlation between these variables, but you don't know what is the correlation. You are not sure about that. Then you know that the function of these two guys, in the dimension sense, is a 0. It's a trivial issue. The number of variables 6, 1, 2, 3, 4, 5, 6. Number of dimensions in this problem is 3, 1, 2, 3. So there are 3 dimensionless quantities I can construct. That's what the theorem, because it's 6 minus 3 in this case. Well, there are some series of rules, but let's look at an example. For example, the recurrent set must contain 3 variables that cannot themselves be formed into a dimensionless group. These are just words. Both L and D cannot be chosen. But they explain why L and D, they don't choose them because they they can be formed into a dimensionless group by itself. Delta P, blah, blah, cannot be used, blah, blah. Anyway, they select three variables. You have to select three variables, D, V, and P. And you know the units. Actually, D is length. Actually, this is length. There is an error here. Velocity is length divided time. And pressure, well, this is N divided L cubed. Then you can solve, you can find the units as a function of D, V, and P, like this. L is a function of D, mass is a function of this, time, you are just solving this here. Solving. You can see this. The solution of this, let's do it here on the board for clarifying. As I say, this is most for class A, but I want to show to everybody. Class B is optional, but let me show you. As I say, there's an error here. This is L, actually. This is L. That's why L is equal D here. If you solve M here, it will be P dq. Why? Because D is L, and you replace by dq. Okay, let's write here. P is equal M L minus 3. L equal D. And B L T minus 1. Then I want to solve L, N, and T as a function of the original variables of the problem. So the first one is trivial because it's solved already. This is solved. Okay? But then I can put this L as D here, because it will be D to the minus 3 here. Then of course it will be P equals D to the minus 3 and N like this. So P D cube N, which is this. You understood what I did here, no? I replace this here, and I just solve it. So you have this. Now you have, I solved this, I solved this. And now you have to solve the time also. For solving the time, you go here, P, L, B. And L is D, right? B to the minus 1 is 1 over B. So trivial, no? So now what I can do is just to express those variables. I mean, I can start to create dimensionless quantities. For example, delta P has the dimensions. These are the dimensions of delta P, I know. And I want to create a dimensionless quantity with delta P. What should I do? Divide by these dimensions. If the dimension of delta P is N, L to the minus 1, and T to the minus 2, obviously, if I multiply delta P by the opposite units, N to the minus 1, L, and T to the square, this quantity is dimensionless. This is a dimensionless. But I want to express it as a function of the variables of the problem. You can see N is PD cubed, L is D, and T is D divided D. So at the end, you obtain this expression. The first dimension is quantity, delta P divided PV squared. This is a dimensionless quantity. Remember M? Remember M is what? PD cubed. So M to the minus 1, PD cubed minus 1. L is what? D. And T is what? dV minus 1. dV minus 1 to the square. So at the end, you multiply this, no? This is 1 over P. That's why 1 over P. This is D to the cube, but in the denominator. it will cancel 1 here, and it will cancel the square here. So D disappear. And B minus 1 to the square, it goes to the denominator, B squared. And delta P was here since the beginning, so no problem. So you have this dimensionless expression. This dimensionless means it doesn't matter which problem you analyze, which prototype you analyze, what is the dimension of the prototype, as long as it's proportional, then we have the same dimensionless number. I'll give you an example. The Eiffel Tower in Paris is double the size of the Eiffel Tower in the Parisian. And how do you know that? I think it's 1/2, right? How do you know that? How did they construct it? Because they use these dimensionless numbers. And they just, with those dimensionless numbers, they know the proportions of the size, and they can design exactly the replica outside. So dimensionless numbers are important. We have 1. We selected as the second dimensionless variable this 1, the length divided D. This is dimensionless. And the third one is this, mu dVp. Okay, this is related to the viscosity, blah. This is the dimensionless in units, and we apply the same process because n is p d cubed. Then you have 3 dimensionless quantities. Then at the end of the day, those are the dimensionless quantities which define the functional dependence. You will have a function of one dimensionless quantity, another dimensionless quantity, and another dimensionless quantity. But you want to solve one variable in terms of the other. So at the end, I decide to solve this delta P divided PV squared, which was actually the first one, which I solved, as a function of the other dimensionless quantity. So I know already at the end of my experiments, I know that my expression, I will write here, delta P divided PV squared will be a function of L divided D and B, P, D, mu. And then you will tell me, but this was mu divided dPd. No, it's the same. This is also dimensionless. You can exchange if you want. It doesn't matter because at the end, the units on the left and the right has to be consistent. Then after, what you do is to play. I mean, this will help you to design experiments. For example, which experiment you can design here, okay? You can analyze, you can fix these variables here, this dimensionless quantity here, and see how this changes with this. Then you will have one experiment where you roll delta P PV squared versus L divided D. Data, blah, blah. And then, it's linear. Okay, it's linear. If it's linear, then you will have delta P PV squared is proportional to L divided D because it's linear. And then now I fix L divided D and I want to analyze the dependence with D P D divided mu. Again, data, I take something like this, very strange, quadratic. Let's assume something crazy, quadratic divided mu to the square. And then I evaluate the units. The units of this guy has to be proportional to the units of this guy. And this is where I start to evaluate, this is land, whatever. Well, take into account that these are dimensionless quantities anyway. So the units doesn't matter at all. So that's the idea. Then at the end, this just is an equality. Yeah? But at least this, of course, this will not tell you the final expression, but it will tell you which experiments you should carry out. It will tell you, there are cases, for example, there are things you cannot change. Let's assume you are going to do an experiment in this room. You cannot change the dimensions of the room. You can say, I duplicate the volume of the room. No, you cannot. So even if that variable appears in the problem, it will be fixed forever. Fixed. If you want to duplicate, you have to use another room, which is the double of this. There are things you can change in this classroom. The position of this guy, you can change. The location of the laptops, the position where you are located. These things you can change. Other things cannot be changed. So the Buckingham methods only tell you which experiments you can carry out, which data you should collect, what is relevant to study, and you don't waste so much time. Because sometimes, of course, what is the most expensive in research? What is it? Wasting time and wasting money carrying out unnecessary experiments. So if you don't do this professionally, you can finish doing experiments which are completely useless. So that's why it's very useful to analyze this thing. So I will share with you the Buckingham method with some examples later. There are more examples, but I didn't want to abuse in this class because we're almost in the break. Then right now, we will do something. We will go to break. This is the plan. Break. And after the break, I will put an activity, easy, to everyone. And that activity is from the previous lessons, not from this. But still is related to your research field. So that's it. We go to break now. I think this is, oh, my battery. So then I will start sharing here, just on time, right?